Welcome back, everybody. In this video, we're going to break down the starting points of a proof, right? Our deductive reasoning arguments. So earlier we said there's things we assume, right? Things that were given that we know to be true. But in addition to the things we're told, hey, for this problem, assume this to be true, right? Because, we don't always assume everyone's telling the truth or lying, right? We also have the things that we just always kind of know are true, right? If you're working in geometry, some things are true. If you're working in algebra, some things are true. If you're working in economics, some things are true, right? Every field, every context has its own things we just assume to be true. Sometimes you assume a lot of things. Sometimes you assume very little, right? So we're going to talk about some of the things we assume to be true in math, specifically algebra and geometry, right? And how we can see those things connect to other stuff. So these things that we assume to be true are what we call axioms and postulates in math. On the right, you can see Thomas Jefferson, American philosopher, saying we hold these truths to be self-evident, right? Discussing at the beginning of the Declaration of Independence the things that they assume to be true. That all men are created equal, they're endowed by the Creator with unalienable rights, and that among those rights are life, liberty, and the pursuit of happiness. So these things that we assume to be true, right? The self-evident things, they are the axioms of the Declaration of Independence, the starting place for their argument that the America must declare independence because they hold these things to be true. And well, Britain is acting in a way that is denying these things, so they therefore must disagree and leave. Now, in algebra and in mathematics, we have our own things we assume to be true, right? Stuff like properties, as we're going to discover shortly, which are the things that we just know are true in algebra. And in geometry, postulates are a kind of axiom, a thing we hold to be true, like a rule, right? But postulates tend to be specifically for objects or for things like segments and angles and stuff like that, shapes. Axiom is a more broadly useful term because it describes rules in general, usually for more abstract things like numbers or equations. So as we can see here, right, we have these things that we assumed to be true, self-evident. Why is Thomas Jefferson saying we assume these things to be true, that they're self-evident? Because usually self-evident means everyone can agree it's true, right? Well, it's important to say the things we assume to be true because not everyone will agree with those assumptions. Remember what we said, that in deductive reasoning, if everyone agrees with your starting place, they must agree with all of your steps and the ending, right? Well, there's the catch. Not everyone will always agree with the assumptions you make. So you need to lay those out at the start. We need to be very clear about what assumptions we use and when, right? That's why when we're doing a two-column proof, postulates and axioms go in the reasons column so that people know the things we're assuming to be true for this problem. And that way, if they don't agree with that assumption, they will know it doesn't hold true for them. So let's look at some of the example axioms and postulates in math and geometry. We're going to kind of blitz through these real quick, right? So some of the ones that really catch people are the properties of equality. These are algebra properties that are a form of axiom when used in algebra. The addition, subtraction, division, and multiplication properties. Okay, so looking right here, you probably can tell what's the solution to this equation? Well, if 2x equals 4, then x should equal 2, right? We just kind of know that. Now, when we're working with equations in mathematics, what we would call algebra, if you remember from middle school, is the ability to manipulate equations, right? To do things to them. But you can't do anything you want. I can't just add 100 over here, right? If I did that, now x wouldn't be 2. X would be something very, very different, right? So that's not what we're allowed to do. We can do anything we want as long as it does not change the truth of the equation that x equals 2, right? That 2x equals 4. So how can we change this equation? What are the things we're allowed to do while still keeping the two sides equal? Well, I could add 100 if I also balanced it by adding 100 to the other side. That is the addition property of equality. Because now 2 times 2 is 4, 104, right? And then 4 plus 100 is 104. So it stays equal. You see, the addition property of equality is the assumption that I'm allowed to add things to both sides. Do we need to prove that? No, right? Because we're assuming it. That's the key to a property. We assume it's true, and then we can just use it as if it's true. There's no need to prove that you're allowed to add something to both sides. Now, what if I was to subtract 100 from both sides? Well, subtraction is really just adding negative numbers, right? So once again, that is something I'm allowed to do. I can subtract a number from both sides. Okay, so now what if I was to say, well, instead of subtracting, what about the other operations we can do? multiplication and division. Well, actually, what you probably did to find x equals 2 was divide both sides by 2, right? And notice if I divide both sides by 2, it doesn't change my answer, that x equals 2. So once again, the division property of equality is something I'm allowed to do. I can divide both sides by the same number, and it will not change the equality of those sides, right? It'll make them look different. Now it's x equals 2 instead of 2x equals 4, but they're still equal. Lastly, the multiplication property is I can multiply both sides. So in this case, I can multiply this side by 6, for example, and multiply this side by 6. I would get 12x equals 24. And once again, I can still see that x would equal 2, right, to make this statement true. So the equality of the two sides is not changed. These two sides remain equal in the same way, right? But I couldn't, again, I couldn't multiply these sides by different numbers. That's not what the properties of equality say. I have to multiply both sides by the same number for the equality to hold, right? So for all of these, if I do an operation to both sides, with the same number, the sides remain equal, right? Those are the properties of equality. Now there's a couple more properties we equip ourselves with in geometry and in algebra. So not just these properties, but some more tricky ones. Let's look at some of the trickier algebra properties. The transitive property. So again, public transit systems, you might have been in class when we did our quiz, right? Any two things equal to the same thing are equal to each other. So I like to think about it like this. If I was to say the USA, right, that's the same thing as saying the US, yeah? And the US is the same thing as saying the United States, right? So really, if I know USA is the same thing as saying US and US is the same thing as saying United States, I also know that the USA means the United States, right? There's actually lots of different synonyms, if you remember. And that's what the idea of a transitive property is, linking things from one thing to the next. Another good way to see it, again, using the transitive property idea, right? If I was to get on the bus at, say, the A stop, right? And I was to go from A to B, right? Get off at the B stop, and then I go from B to the C stop, right? Well, I don't really need to have told you all of that, right? I could have just said that means that A equals C, that I got on at the A and got off at the C. I didn't need to tell you about the B stop in the middle, right? Because I got off at B, then I got on the B and went on to C, right? It was just a little stopover. I didn't need to say that bit. I can connect them right across the middle. If I was to lay this out as A equals B equals C, I don't need this step in the middle. I can just say A equals C. That's what the transitive property means. All right. So now the substitution property, any two things equal to the same thing are equal to each other. So if I was to say A equals B and C equals B, then I know that if A equals B and C equals B, then I could say A equals C, right? Sounds kind of like the transitive property, so let's put it in a different way. If I was to say X plus 6 equals Y, man, I would sure love to know what Y is. Well, if I know what X is, X equals 2, let's say, then I know that means 2 plus 6 equals y, right? Now I can know what y is. Y would equal 8, right? Even though x is 2, it is 2. That didn't change anything. Sometimes being in a more useful form allows me to solve other things. X wasn't helpful over here, but once I know x is 2, then I can say 2 plus 6 and get 8, right? So the substitution property allows us to replace things with other things they're equal to. As you can see in the pictures, think about it like Naruto or Pokemon or Indiana Jones, where they replace something with something else, right? Make a more useful something else in that given context. Okay? So now, two of the quicker ones, the reflexive property, all things are equal to themselves, okay? So Spider-Man is Spider-Man. Obviously, there are two Spider-Men here, which gets them a little more confusing, right? But that's the same thing as saying, I got my spider, and that's equal to my spider, right? Or likewise, 2 equals 2. Not a really impressive property, right? It does come up, though. Lastly, the symmetric property. If two things are equal, it does not matter what side of the equal sign they are on. So in this case, I have a block which is equal to 4 gold coins. Well, the block happens to be on the left side of the scale, and the 4 gold coins happen to be on the right side of the scale. If I was to swap them and put those on the left and those on the right, would it actually change anything? No, they would still weigh the same, right? It doesn't matter if they're on the left or the right. Likewise, it does not matter if I say 2 plus 3 equals 5 or if I say 5 equals 2 plus 3. Directionality doesn't matter for equal signs. That's the symmetric property. I can flip it and it won't change a thing. Okay, so those are the algebraic properties, but we got two more to talk about. The geometric postulates. So these are the things we assume to be true in geometry, and they were going to look tricky, but they're not as tricky as they seem. So the first geometric postulate is the segment addition postulate. The segment addition postulate is that I can click together segments like I'm adding them, right? So imagine, I'm walking somewhere, I'm walking, right? And I go 2 feet, and then I stop, and I go 3 more feet, and then I stop. How many feet did I go total? Well, I went 5 feet total, right? We know that stopping then going again doesn't change the total length of the trip. Likewise here, AB plus A plus BC equals AC, right? It doesn't matter that there's a stop in the middle. That's something we have to assume, though. We know it's true in the real world, but in geometry, we have to assume that to be true, that I can click together segments and make them add it together, right? As long as they're on a straight line together. That's a key thing. They have to already be on a line together. You can also view it as the reverse, right? If I know that the whole trip is 5 feet, if I was to stop 2 feet in, I know I have 3 feet left to go, right? Or likewise here, if I was to add this point B in the middle, I know that A to B and B to C will add up to be A to C. Okay? And then the last postulate, the angle addition postulate, imagine I'm in the shower, I'm in the shower and it's really, really cold and I need to turn down the heat. So I'm going to turn it 40 degrees. Oh, it's still too cold. I'm going to turn it 60 more degrees. Ah, that's just right. And I know that's just right now. So the next time I go in the shower, if I know that 40 plus 60 was just right, how much should I turn it next time? 100, right? Because I know 40, then 60 more degrees is a total of 100 degrees turned. What tells us we know that to be true? Again, real world experience. We just assume it to be true in geometry, but there's nothing that says it must be true in geometry. This is something we assume to be true. So just like we could add segments together, we can add angles together. But again, there is a restriction, right? This point in the middle, D, must, well, be in the middle, right? D must be between A and C. So the angle has to be split in two parts that are adjacent, touching each other, right? If they're off in completely different parts of the world, then I can't click them together that way. Likewise, if I turn and turn again, see how it starts immediately where it left off? That's the key. And there you go. There you have it. That is the geometric postulates added to our list of algebraic properties, which are all forms of axioms, the things we assume to be true in order to use deductive reasoning in math. All right? So this video, I hope it helps out a lot with understanding the things we assume to be true and how we use them in geometry and in mathematics, okay? These are the things that go in the reasons column of a 2-column proof. And next video, we'll see that in a good example using some theorems. If you don't know what a theorem is, I really recommend watching that next video. See you then.